Let's discuss the factors affecting solubility. Okay, before we get to the questions, I want to talk about each of these four situations we had with the inverting the tubes. Okay, and we're going to try to compare some of these to like seats in a movie theater. Okay, see if we can explain why we saw what happened. Okay, so let's say that we've got 100 seats in a movie theater in this first part. If you leave the solution uninverted, it would be like filling the seats in the theater from front to back, one seat at a time. So a person's got to sit in the first seat, then somebody's got to sit in the second seat in the front row, then the third seat, then the fourth seat, then the fifth seat, all the way to the 10th seat, and then they go to the second row and they can fill that way. So they have to fill it in an order from front to back. If you invert the solution, it's like letting everybody come in and pick a seat wherever they want to, because you're exposing all of that water when you invert it to the salt. All right. If you don't invert it, just the bottom layer is exposed to the salt. So the bottom layer of water has to dissolve the salt. It becomes saturated, then it has to move slowly so another layer of water can get down to it. The effect of temperature on the rate of dissolving. This is like changing the numbers of seats in a theater. Most solids have a lower solubility in cold water than they do warm water. And so this would be like, if you have a cold solution, it would be like, we'll just say 100-seat theater, and you've got 90 people that are going to fill those 100 seats. At the room temperature water, now we increase the seats a little bit. Maybe now we have like a 200-seat theater. And we've got 90 people to fill those 200 seats. So it's easier for the 90 people to fill 200 than it is for the 90 people to fill 100. With the warm solution, since it was so much warmer than the room temperature, that would be like those same 90 people having 1,000 seats that they can fill and they can set wherever they want to. The effect of temperature or the effect of surface area on the rate of dissolving would also be like seats in a theater, or be like increasing the seats. So rock salt is going to take a long time to dissolve because, well, let's just talk about it in terms of, instead of trying to define it in terms of the theater, let's talk about it in terms of how things dissolve. So a piece of rock salt, if you can imagine, if we had a big piece, it would be something like that. And what happens is only the outside layer of the rock salt is exposed to the water. So that outside layer has to dissolve before the layer inside of it dissolves, before that layer dissolves, and so on. So the bigger piece of salt you have, the longer it's going to take to dissolve because the more layers it has. Salt crystals has less layers than the rock salt. So you've got maybe a smaller, maybe the rock salt is a piece like this. The salt crystals is a piece like this. And then the powdered salt is a piece like that. And so the salt crystals it's still kind of thick, but it has fewer layers that have to dissolve. And in the powdered salt, there may only be a few layers because it's so small to dissolve before you get everything exposed to the water. And the last one I want to talk about, we'll go back to the theater example, the effect of already dissolved solute. So this would be like, again, if there's no solid in there, it's like people filling 100 seats. We'll say 20 people coming in and filling 100 seats. That should be pretty easy to find a seat, and they can sit down very quickly. But if we've already got already dissolved solute, we said we put 0.4 grams in there, so that would be like 40 people already have seats in there, and then you put another 20 in there, and they've got to find a seat. So now there's less seats. There's 40 less seats for these 20 people to find, and so it's going to be harder for them to find a place to sit. So let's then flip over to the back and answer these questions real quickly about what happened. The first question says, what's the effect of the inverting the test tube on the rate of dissolving? It increases the rate of dissolving. And I'm going to explain it in terms of seats. We'll say it lets people fill the theater from any place. Number 2, what's the effective temperature on the rate of dissolving? Higher the temp, higher the dissolving. More seats to sit in. What's the effective surface area on the rate of dissolving? Higher the surface area, higher the dissolving. And the reason why, if you've got more surface area, you have less layers to dissolve. Number 4, what's the effect of already dissolved solute on the rate of dissolving? It decreases the rate of dissolving because it makes, we already have seats filled. So I'm going to say already have seats filled. So I'm going to erase that, and we're going to go look at 5 and 6. And I'll move it up so we can see those. Why is solvation a surface phenomenon? It talks about this in the background information. It's a surface phenomenon because only the molecules exposed to water dissolve. So the surface of the particle has to dissolve before the next layer inside of it dissolves. Number 6, give 3 examples of solutions you encounter on an everyday basis. List of solute and solvent. Let's not worry about the solute and solvent. 3 examples of solutions you encounter on an everyday basis. We'll say pop, lemonade. I don't know if you drink that on an everyday basis, but Gatorade. Those would all be solutions. Okay, and the solute is what's being dissolved, and the solvent's what does the dissolving. So the solvent is the liquid in this case. The solute would be, well, sugar, carbon dioxide, whatever.